I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Today we will be going into the domain of time series econometrics. The basic thing in time series econometrics is the moment you have a data, you plot it. Plotting the data, although it looks very simple and maybe also naive to some people, but plotting of the data gives you a very good amount of information about what is to be done or what can be done. See, till now, when we were discussing in our things on econometrics, we have been dealing with, like, if you want to find a causal relationship, we can do regression, we can use dummy variables, you can use logistic regression, and you have to just check for the heteroscedasticity, the serial correlation. If there are many independent variables, you check for multicollinearity. You check whether the model is specified and identified, and then you can estimate these estimate the parameters. But one important thing missing, particularly when the data is of time series nature, is the data stationary? Now, stationarity is the essence of, I think, the time series. In my perception, it is the essence of time series and how the data is to be interpreted in terms of time series. We will see now first in our first few lectures, in a series of lecture, we will emphasize on stationarity and we will try to understand the essence of it. We need to be very careful about this. The reason, if our data is not stationary and we have done ordinary least squares, we have done our regression, your estimates of beta hat are not sensical. The relationship may be spurious, and leave alone spurious, you cannot depend upon those parameters. You cannot depend upon that relationship. If the data is stationary, fine. You can very well use your classical linear regression model using the OLS system, and you can minimize the errors and estimate beta. It's very fine. What if it's not stationary? That is so. Now, first in this time series, first you have to learn to identify whether a series is stationary or not, and if it is, then if it is stationary, if we do OLS, if it is not stationary, then we have to go for other methods which specifically come in this ambit of time series econometrics. Examples of it are, say, Johansson cointegration. You have this ARDL method of Pissarro, and then you have the VAR vector autoregressive models, and then you go on to the Granger causality and things like these. So let us start with, say, a graphical representation of the data. Suppose you have this data and it is plotted. We get a picture like this. If this is the type of data, we are very lucky. Lucky in the sense, we will most probably go back to our OLS and estimate the parameters. The next one is, the pattern is the same, or you can say technically the variance seems to be the same, but it is not starting, or that pattern is not around the zero. It is somewhere else. It is above it, with a particular, or like in regression we can say that it is having an intercept term over there. But the movement is the same process like it was in the earlier case. In the earlier diagram, if in the earlier diagram it was it was around 0, but in this diagram it is not around 0, it is around a particular value. We take another case. Now herein it is increasing, and it is increasing, and there is this variance type of trend, or it is around a particular trend, it is going up and coming down. So what we have seen that it can be, it was in the it can be like this with the 0, it can be with like this, and we have seen also it is like this. But our data can be like this also. Now here something is different from the other, and that is this variability is more. The earlier one was like this, say. The variability was same around the increasing trend, but here the variability is different. At different point of time, the variance is different. So these are the probable patterns which can happen with your data. Although these are just hypothetical cases, the exact representation of the data, you need to have the data and plot it and you will find it. But this is just an example to make you familiar that data can be of this shape, or this shape, or this shape, and like this. So what we come from here is, if you see, there are two types of data are presented over there. One is marked as stochastic, effect of the shock, and I am speaking technically, is integrated into the series. The shock has a permanent effect, and that is why we call it also integrated series. But for the moment we say that this series is not stationary. Compare it with the other series, which is more or less going as a straight line. It is called as a deterministic series. Now here the effect of the shock disappears quickly, or technically there is a thing called as mean reversion. But what we need to understand that this series is what we call it as a stationary series. So deterministic and stochastic, we have these two type of series. So now let us come to the definition of stationarity. As this is exact definition has been taken from the book of Damodar Gujarati. It says, a stochastic process is said to be stationary if its mean and variance are constant over time, and the value of the covariance between the two time periods depend only on the distance or gap or lag between the two time periods, and not on the actual time at which the covariance is computed. If we show it in term with notations, expected value of yt is equal to mu, variance of yt is equal to sigma square, and covariance yt minus k is equal to covariance yt plus k. This is a different time period. This is a different time period. This is a different time period. This is a different time period, but your covariance is same. So with this definition of a stationarity, we see the characteristics of a stationary process. It is mean revert. It goes up, but again it comes back to the mean. It has a finite variance. The series doesn't deviate infinitely. The series doesn't deviate infinitely. It has a finite memory. It's not that something has happened and that shock, it keeps on memory and it keeps on behaving accordingly. That effect of the shock, after some time it will die out. Yeah, memory is short term, it's not long term, that some impact has happened and I keep on remembering it for a longer period of time. So the characteristics, it's mean reverting, it has a finite variance, it has a finite memory, and the shock dies out with time. Now this non-stationary data does not only mean a sustained increase or decrease. We have to understand this. Okay, what we are saying, this goes up and it comes down, it's fine. But we have to be careful that non-stationarity does not only mean a sustained increase or a sustained decrease. It also implies a sustained walk in one direction before moving to the other direction. And so, as an example, if you refer to there is a person who is a drunk. So if he is moving in a wide open park, the park is very big and it has a lots and lots of ground. Now he will move like this, he will move like this, he will move like this. So there is no trend. It's not necessary that, what I want to emphasize over here is non-stationarity does not mean only that there is a trend. A sustained walk in one direction and again changing to the other direction, this also means that the data is not stationary. What is the impact of this stationarity? First is on the behavior of the time series. If time series is stationary, the effect of a shock will be short-lived. It does not have a permanent memory. And if the time series is not stationary, shock has a permanent effect and the shock is integrated into the series. Then regarding the chances of spurious results, see, if two time series are not stationary, we will get a significant relationship between variables even if they are not related. We may get a significant relationship between variables even if there is no relationship between them. And then regarding the significance testing also, if the time series is not stationary, the standard assumptions of t-test and f-test, t-test is used to estimate the significance of the parameter and f-test is used to assess the significance of the entire regression model or the significance of such the R square. So these t-test and f-test will not follow their standard respective t distribution and f distribution. So there can be problems with significance testing, there will be issues, we may find a spurious regression, and then the behavior of time series is different in both the cases when the data is stationary and when it is not. In the terms of stationary, the data mean reverts, whereas in terms of non-stationary, there is a permanent shock into the series. To explain this concept of stationarity, what we do, we take the first example of random walk models. Here this is the case that there is no sustained movement, there is no trend it is going, there is no explosive trend and you can see that and say, see, this data is not stationary. What we find, there is sustained walk in one direction, or then again it changes to the other direction, and then see whether these type of models they are stationary or not. We will be proving it. The examples of random walk model could be stock prices. This is a classic example of stock prices. According to that random walk hypothesis, stock prices exhibit no predictable trend and follow a random path. This means, the implication of this is that the future movement of stock prices cannot be reliably predicted based on past prices alone. Also, similar thing you will find in foreign exchange rate markets also. While although there are many factors which influence foreign exchange such as interest rate, inflation, geopolitical events, but the random walk theory suggests that the short-term movements in exchange rates are unpredictable and follow a random pattern. Now here we will see for three different type of random walk models. One is the simple one, the simple random model wherein no drift, no trend, and then Then we will see the next model where there is a drift, and the third model where there is a random walk with drift and trend. Now we take an example, the first one, which is a random walk without a drift. Yt is equal to yt minus 1 plus epsilon t. Today's thing, it depends upon what happened in past, what happened yesterday, plus an error term epsilon. Basically here, this is a special case. We can write it as, if we write it as yt is equal to theta yt minus 1 plus epsilon t. Now if you say that this theta is equal to 1, we can simply write this model as yt minus 1. So we assume that say a process is starting at time t, then y1 is equal to, so yt minus 1 in place of when y is 1, and then t minus 1 will be 0 plus epsilon 1. Then what will be y2? Y2 will be equal to y1 plus epsilon 2. Now y1 we have just now got the value, we incorporate the value of y1 over here. So what is left is y0 plus epsilon 1 plus epsilon 2. Fine. Then we next move to y3. Y3, it will be based on yt minus 1, it becomes y2 plus epsilon 3. So this we can write it as, now y2 we have just now defined over here, as it is we write it down plus epsilon 3. From here you take epsilon 3. So it becomes y0, y0 plus epsilon 1 plus epsilon 2 plus epsilon 3. This can also be written as y0 plus a summation of epsilon 3. The summation of epsilon, not exactly 3, because we are now adding this, so we just say epsilon. But excuse me, 3 here means 3 times the error has been added. Now next, again, so we write the general model as yt is equal to yt minus 1 plus epsilon t, that is equal to y0 plus epsilon 1 plus epsilon 2 plus epsilon 3 extending up till yt. So we can write it as this AR model as y0 plus summation epsilon t. Now we, using our knowledge of taking expectation, we take this expectation. So expectation of yt is equal to expectation of y0 plus epsilon t. Now we write it separately, expectation of y0 plus expectation of epsilon t. Expectation of epsilon t is an error term, is equal to 0. So what you are left with? Expectation of y0, and what is the expectation of y0 is equal to y0. The reason that expected value of a constant is the constant itself. Now, so mean, we are saying up till we have just studied the done the mean of it, that is the expected value, and we find that okay, from this we cannot say whether this is stationary or not stationary, because it seems to be constant. Now we go to the variance. The formula for variance is expected value of yt minus expected value of yt, the whole square of it. So this we have just now seen that what is expected value of yt is nothing but y0, and what is the value of yt? Yt is equal to y0 plus summation et. We have just now proved these two things in our previous slide. So now, so this, in place of this we write this, and in place of yt we write this. This y0 and y0 is cancelled out. We are left with expected value of summation et, the whole square of it. So summation et square, we write it as, because there is an element of t, we have how many times the t sigma square epsilon. So what we can see from now, then element of time is incorporated over here. So we can say that the variance is a function of time. Now, if this is the characteristic of because what stationarity requires? Constant variance. It was constant mean. Okay, fine. Constant mean is there. That the second condition was constant variance, and what we see over here, the variance is not constant. There is an element of t associated with it. So as the time will increase, the variance will also increase. So in the case of random walk, effect of a shock doesn't die out. It has an infinite memory. The shock is integrated into the series. Based on what we are saying, based on that, the variance of it depends upon time, meaning thereby this is a non-stationary process. So the first model, random walk without drift and without trend, is a non-stationary process. So there is a persistent, we are just discussing the characteristic. There is a persistence of shock, and effect of shock is integrated and has an infinite memory. If you assume y0 is equal to 0, then yt is nothing but a cumulative shock, a cumulative sum of all the previous shocks, and in the process the effect of shock will not die out. These are some of the things which takeaways from this discussion on random walk model without drift and without a trend. Now, we take the second model, random walk with drift. So here what we are doing, we are incorporating a drift parameter alpha, similar to your intercept in a normal language of regression. So yt is equal to alpha plus yt minus 1 plus ut. Now y1 we can define as, based on this, alpha plus y0, because we will take a period back. So if you period first, then in the earlier period was 0. So alpha plus y0 plus u1, y2 what we do, it is alpha plus y1 plus u2. Why y1? Because 2 minus 1 is 1. So this y1 we have this value. So we write that. So it is alpha plus y0 plus u1 plus u2. Similarly, we do the same thing for y3. y3 is equal to alpha, the intercept, plus y2 plus u3, and y2 is this. So we write this alpha over here, and then for this entire up till here is nothing but your y2. So alpha plus y0 plus u1 plus u2 and y3. So if I want to write it in a general format, I can say yt is equal to alpha times t. There are 3 alphas, so we write here alpha times t plus y0 plus summation of the error term. So this is what we can write as the general form of this series of random walk with a drift parameter. So if you take the expectation, at comes as it is because it's a constant term, y also comes as it is, expected value of ut is equal to 0. So what we find, in the mean itself there is a time element, meaning thereby mean depends upon time, meaning thereby the expected value depends on alpha t and it is deterministic. In the previous case, mean was fine. From the mean, it didn't give an impression that it is a non-stationary series. Only when we calculated variance we came to know about it. But in this series, that is the random walk with the drift, in the mean only we find that there is a time element. Then we go to let us also check the variance. Variance, we have seen the formula is expected value of yt minus summation yt, then the bracket close, the whole square of it. Yt, we know what is yt. Yt is equal to alpha t plus y0 plus summation ut, and expected value of yt. What happens? This ut disappears because expectation of u is equal to 0. We write all those things. So in place of yt we write alpha Now, once we open the bracket, then alpha t and alpha t gets cancelled, y0 and y0 gets cancelled, so we are left with summation ut. So, summation ut square, again summation u square is sigma, fine, but there is an element of time t. So, this indicates that the variance is t sigma square u. It means there is an element of time over there. So, the variance also depends upon time. As the time changes, the variance changes. So, this process is non-stationary. Although we came to know that this process is non-stationary when we had derived the mean value, but we just did under variance. But so the final thing is, this process, that random walk with the drift, is a non-stationary process. Now let us take the third case, the third and the final case of random walk. It has a drift element and it also has a trend. It has a drift and has a trend. So we write the drift as mu. We write the drift as mu, and this bt is nothing but this mu is your drift, and this bt is nothing but your trend value, and then your normal that you from the simple random walk you had yt minus 1, then with accompanied with an epsilon t. So y1 is equal to, if I take y1, so mu plus 1, this is not beta 1, this is 1 means 1 beta t plus y0, because for t minus 1, if t is equal to 1, t minus 1, 1 minus 1, it will be 0, plus y0 plus epsilon 1. Next time, y2 is equal to mu plus 2 bt plus y1 plus epsilon 2. So now what we have done, in place of y2, in place of y1, we will incorporate this entire thing of y1, this entire numbers of y1, see they are incorporated over here. So it becomes mu plus 2 bt plus mu plus 1 bt plus y0 plus epsilon 1. These are the terms of y1 plus epsilon 2. So if I now if I just join the similar terms and do all the additions and all, so what we find, y2 is equal to 2 mu plus 3b plus y0 plus epsilon 1 and epsilon 2. Now let us go and find the value for y3. y3 is equal to mu plus 3bt, because time t, plus y2 plus e3. So for y3 we will have y2 over here, and the value of y2 we have just now derived. This is the value of y2. This value we are writing it incorporating it in the equation of y3. So y3 is equal to mu plus 3bt plus 2 mu plus 3b plus y0 plus epsilon 1 plus epsilon 2 plus e3. We opened the bracket and put this the similar terms together. So what we find, y3 is equal to 3 mu plus 6 bt plus y0 plus e1 plus epsilon 1 plus epsilon 2 plus epsilon 3. So now there is an element t associated with the drift parameter. There is an element t associated with the trend. So now what if we want to define it? If you want to write the general form of it, so the general form reads as yt is equal to t mu plus, in the numerator, t bracket t plus 1 bracket close divided by 2 multiplied by beta plus y0 plus summation et or summation epsilon t. So here while finding the mean, and the expected value of this will be 0, but this value is there, this value is there. So when we have once we have calculated the mean or derived the process for the mean, we find that there is an element of time over there. As the time changes, these in the t also, in the drift also there is a mu, in the trend also there is a t. So this is not a stationary process. the mean is not constant. Mean 0 is a special case, we are not talking about that, but our mean is not constant. If our mean is not constant, then our process is not stationary. So, but one thing, just understand, we are referring to its mean, but this is mu is not exactly the mean of the process. Rather, it is a variable which determines the mean of the process. Now, so what we want to say is, the final takeaway from this discussion is that a random walk model with drift and deterministic trend, the mean of this series depends upon time. So, this series is not stationary. So, what we started today's lecture, we will be stopping here. We started today's lecture with the discussion on stationarity, and then we have seen how various the data visualizations can look in different cases. Then today we discussed a case particularly of random in the purview of random walk models. We have taken 3 random walk models. One was the simple one, the second one with a drift parameter, and the third was random walk with a drift and a trend element. And we have seen that in the first case, the mean was okay, the mean was constant, but the variance was it changed with time, was not constant, so it was not stationary. The second model, that is the random walk with drift, here the mean itself was not constant, and so it was not stationary. And the third model, that is the random walk model with drift and deterministic trend, here also the mean is not constant. So we can say that this is also a non-stationary process. So all these 3 random walk models of random walk are non-stationary in nature. Hope this lecture is clear to you. Thank you.